Hey guys, in this video, we're going to talk about techniques of estimation of population parameters. As we mentioned before, the goal of statistics is to um, select a smaller group from a population, study that group, and project our findings onto the larger population. So in other words, we are looking at the statistic from the sample, and goal is to target a population parameter. Okay, so I would like to start with an example. Let's say I have a friend who lives, I don't know, maybe in Texas, and she wants to come to San Diego, and she wants to know the prices of gas in San Diego because she has a big truck. So I have two options. First of all, I could ask my students, let's say, what was the price of gas when they purchased their gas last time. Uh, write down all of these gas prices, find the average, and tell her. Let's say the average was $5.25. So, and I will tell her, the gas of price right now is $5.25. That would be an example of a point estimate. So the point estimate is a single value or point used to approximate a population parameter. Now, the question is how accurate that estimation will be. Imagine that she comes with her truck and then she fills her tank with the gas. And every time she does that, she records the price of gas. And then at the end of her trip, she calculates the average price. The question is, what is the probability that her average price will come out to be $5.25? And I hope your answer is the probability of that is 0, right? So then another option for us would be, instead of giving her a specific price, we could give her a certain interval. Let's say, I would say the average price is between $5 and $5.50, for example. That would be an example of an interval estimate. So an interval estimate is a range or interval of values used to estimate a true value of a population parameter. Okay, now this is just an interval estimate. This is not a confidence interval yet. But before we do that, I would like you to I would like to offer you to take a look at two examples first. Suppose that the mean for the current gas price is $6.5 with a standard deviation of 25 cents. Suppose that you obtained prices for the premium gasoline from 40 randomly selected gas stations. Okay, so now we're talking about a sample of 40, not a single selected gas price. Okay, so construct an interval that will contain 68% of all sample means. And now we're in a central limit theorem territory, right? Where the mean of the distribution of the means is the same as the mean of the population, which is still 650. But the standard deviation is this of the distribution of sample means is the standard deviation of the population divided by the square root of the sample size. So in our case, it's going to be 0.25 divided by the square root of 40. And what is that going to be? That is approximately 0.0395, or let's round it to 2 decimals. It's going to be 0.04. Okay, so that's our standard deviation for the distribution of the sample means, because we know that a sample, it targets the population mean better than just one selected value, right? So the average of 40 will be closer to the true mean of the population than just one randomly selected value, right? That is why our standard deviation for the distribution of sample means is way shorter than the standard deviation for a single selected price. Okay, so what do we have? Let me write down the values on the bottom of this distribution. So for the mean, we still have 6.50, but one standard deviation to the right is going to be 6.50 plus 0.04, which will give us 6.54. And plus another standard deviation will give us 6.58, and one more 6.62. Now, if we're going in the other direction, we're going to have 6.46 and 6.42, and then 6.38. Okay, so if we want to catch 68% of all the gas prices in the means of the sample of 40, that's going to be an interval from 6.46 to 6.54. So that would be the answer to question A. The answer to question B, if we want to catch 95% of all sample means, then we would go from 6.42 to 6.58. Okay, so this is the interval that contains 68% of all sample means, and this interval contains 95% of all sample means of premium gasoline prices of size 40, given that these are the parameters of our population. And I want to mention again that we're not estimating the parameters of the population yet. We are given the parameters, and we are building the confidence intervals for those sample means. So how close are those sample means of size 40 to the mean of the population? Pretty close. And what I want you to realize that if a sample mean is close to the true population mean, what that also means is that the population mean is also closer to the sample mean, okay? And that's the transition. This is what we're going to use to estimate population parameter. I'm going to repeat that again because that's important. If the sample mean is close to, and we could put a percentage on how close it is, like for example, for 6.54, that's 68% chance that it's close to the mean of the population. In turn, that means that the mean of the population is that close to the mean of the sample. All right, so we're gonna look for the mean of the population around the mean of the sample, because in real life we don't have the information for the population. We only have the information for the sample. So when we, and keep in mind that the larger the sample, the better estimation we get. So the larger the sample, the closer value to the population parameter we will get. But it's sometimes it could be very expensive if we want to get a large sample. For example, if we want to test the durability of a car, what car manufacturers do, they crash the first cars to see how safe they are, to estimate their safety. So and those experiments are expensive. We don't want to crash, of course, all of the cars, so we have to establish the minimum amount of cars that we can crash in order to get reliable enough information. So that will come up to how large of a sample do we have to have in order to guarantee a certain accuracy of our results. That's another objective that we're going to be looking at in this unit.